So Bex used the basilar membranes isolated from cadavers, and his results showed that no difference in response for close frequencies that people can distinguish. So he wasn't able to detect that. He wasn't able to show, the difference between 1,000 hertz and 1,200 hertz, or 1,100 hertz, or even 1,000 hertz and, let's say 1,000 hertz and 1,100 hertz. We can detect that difference. Most of us can. But he had a hard time detecting that with his cadaver. He wasn't able to show that there were cells that would respond differently. He couldn't do that. And remember, he was using cadavers, though, so he was using slightly damaged membranes. But we have new research with live membranes that shows that live, healthy membranes, the entire outer hair cells move, can move back and forth, and they'll change their length and tilt back and forth. And so what they do, these cells are called a cochlear amplifier, because they're able to change their length and essentially take the energy. The outer hair cells can take the energy that's being vibrated and amplify it, essentially, so that you can have a better detection of those very small differences in frequencies, for example. And here's the way they work, right? So what they'll do is, not only do the hair cells move, but when the membrane move, the cell stretches and contracts. It stretches and contracts. So that movement, not only of the hair cells, but also of the stretching and contracting, that movement is used to detect very small changes in frequencies, or very small changes in vibrations. And we see the effects of the outer hair cells by looking at this very stark description right here. The blue line indicates a normal threshold curve for a particular frequency. I guess this frequency is about 8 kilohertz, right? So 8,000 hertz, and it's right there. And so it obviously we can hear it, right? We can hear it at a very low threshold. It's detected at a very low threshold. But when the outer hair cells are destroyed, nothing. We can't hear anything, because of the fact that those outer hair cells are being used or act as an amplifier for certain frequencies. If you remember Newton's prism, a prism is a little piece of glass that if you were to take white light and shine it through, it breaks up that light into the primary colors of the rainbow. You can think of the basilar membrane as an acoustic prism that takes white sound, right? Sound that's a mixture of different tones and frequencies, and breaks it up into its constituent frequencies. That's one way to think of the basilar membrane. When you're watching the basilar membrane vibrate, there's peaks in its vibration that correspond to the harmonics. So if you were to play a complex tone with the fundamental frequency and all of its harmonics, you can actually see the peaks at each one of the harmonics. And here's a complex tone with the peaks at each of the harmonics. Harmonics at 440, 880, and 1320. And you can actually see that vibration in the basilar membrane, the same pattern of vibration. So in this way, the basilar membrane is taking this complex tone made up of 3 harmonics and breaking it up into its basic parts in much the same way that a light prism takes sunlight and breaks it up into the individual colors of the rainbow. All right, so let's go into a little bit more detail on how these nerve fibers work. There's a concept of phase locking. Phase locking basically it's a relatively straightforward concept. It basically says that neurons fire in response to particular pitch and particular frequencies and particular amplitudes, right? So these nerve fibers fire for, these frequencies, and these nerve fibers fire for these other frequencies. That's phase locking. These nerve fibers fire in bursts. So they will be stimulated by a particular frequency, and they will fire a burst of activity. The bursts happen at the peak of the stimulus. So when the stimulus goes up, they'll fire like crazy, and when the stimulus goes down, they won't fire. When the stimulus goes up, they'll fire like crazy, and when the sine wave goes back down, they won't fire anymore. They're locked in phase with the sine wave. So groups of fibers will fire with a particular pattern, then they'll be silent, then they'll fire, and they'll be silent, and this creates the patterns of firing that have to ultimately be translated by the brain. But we believe it's these patterns of firing that probably lead to our perception of pitch. Right? Lots of bursts coming close together is perceived as high pitch, and not so many bursts further apart is perceived as low pitch. And once again, we go back to this model that we were exposed to in Chapter 1, this relationship between the outside world, the stimuli, the meat, the physiology, how it works, and then what our mind perceives, right? So the stimuli affect the physiology, obviously. So stimuli affect the physiology by timing. So the firing rate is determined by the frequency and periodicity. So phase locking. So high frequency is a high firing rate. And of course the place, the location on the cochlea. So stimuli affect the timing of the bursts of neurons as well as where the cochlea vibrates. The stimuli obviously also affect our perception, right? So pitch is related to the frequency and the periodicity. So how fast it's coming and how loud it is. High frequency and high periodicity equals high pitch. So very high frequencies equals high pitch. We perceive it as a high pitch. Now, the relationship between physiology and perception, in other words, what's the relationship between how the mechanics of our ear work and what we perceive? Well, that involves the phase locking. Phase locking occurs below 5,000 hertz. Perception of melody occurs below 5,000 hertz. So we really can't perceive things as working together as a melody above 5,000 hertz, because at that point it just becomes a cacophony of lots of energy being thrown at you, right? So we have this theory, right, this place theory, right, where we have your basilar membrane, and wherever it vibrates is what you're going to hear as a pitch, right? So low pitches, high pitches. Well, it turns out that's not entirely everything there is to it. And the reason for that, one of the things that we found is that for sounds above 5,000 hertz, so 5 kilohertz, we don't perceive melody above 5,000 hertz. So a melody like a song or an orchestra playing. Anything above 5,000 hertz, we perceive it, but it doesn't sound like a beautiful melody. It just sounds like weird sounds changing. If you were to measure all the sounds generated by the instruments in an orchestra, None of the instruments goes above 5,000 hertz in their fundamental frequencies. None of them do. They're all below 5,000 hertz. So there's something going on in our perception of pitch other than place coding, because if it was just place coding, then it wouldn't matter. We would be able to perceive melodies no matter what. But there's some breaking point at 5,000 hertz that is causing us to be able to perceive much more rich and complex sounds like orchestras below 5,000 hertz as opposed to above 5,000 hertz. And we have discovered that temporal coding with phase locking, so this ability to lock hairs into phase with the timing of different frequencies, is also important. So it's not just the place where things are vibrating, it's also when they vibrate. At what point in time do the hair cells vibrate? And that sort of temporal coding with the phase locking is probably important in helping us to perceive things like melodies. All of the hair cells are connected to other neurons that ultimately bundle up into the auditory nerves, and those auditory nerves project to parts of the brain stem and reach the cortex in the primary auditory receiving area here in the temporal lobe. So this is a cartoon drawing of a human brain. So this is a human brain of a person that's looking in this direction here, looking off to the left. The eyeball would be about here, and this is the top of the head, the back of the head, and this is the side. So we're looking at a side view of the human brain, and the outside of the brain is the cortex, of course, so the human brain is the cortex, and this right here, this spot, is where the initial auditory receiving area is located. We actually have it mapped out. We have been able to map out this auditory receiving area, and have been able to map out certain spots where certain frequencies generate the highest responses. So 20 kilohertz, 8 kilohertz, 300 hertz, etc. All of these spots here maximally respond to these particular frequencies. We can actually relate the inputs of stimuli to responses in this part of the cortex. So, for example, if we play these three frequencies here, we'll get this response. This set of frequencies here, this response, etc., etc. Very nice mapping. So you can damage your hair cells. Your hair cells are very sensitive. Presbycusis is a damage to your hair cells by exposing by listening to too many very loud, dangerous noises. You lose mostly hearing at the highest frequency. So anything above like 10 kilohertz is hard for you to hear. It affects males more severely than females for some reason. And it appears to be caused by exposure to damaging noises like really loud jet engines, lots of rock concerts, or by certain drugs. There are certain drugs like if you're allergic to aspirin, for example, you can cause damage to your hair cells. Here's an example of some hearing loss across time with men and women. So here we have the ability to hear. The higher the curve, the more sensitive you are to what you're listening to, because it goes from 0 decibels to 100 decibels. And then along the x-axis we have frequency. So these are the three curves for three different ages of people: 50 to 59, 70 to 74, and really old people, 85. And as you'll notice here, you'll notice first of all there's an effect of age. As we get older, our hearing tends to get worse, which you can see in a decrease in both curves, going from 50 to 59 to 85. Our hearing is less sensitive across pretty much all the frequency spectrum, going from low all the way up to 8 kilohertz. But there's also an effect here of sex. Notice that men tend to lose their hearing more than women do. All kinds of reasons for that, all kinds of jokes you can make about that, but bottom line is that men and women lose hearing as a group differentially as they age. So loud noise can severely damage the organ of Corti. As a matter of fact, it's a serious problem. OSHA, the regulatory agency in the United States that governs workplace safety, has standards for noise levels at work. So if you work, for example, in a factory floor with a lot of very loud equipment, you're required to wear ear protection. If you're one of the guys on the tarmac at the airport that works around loud jet engines, you are required to wear ear protection. Obviously, leisure noise can also cause hearing loss. We have a lot of hearing loss that's happening now in young people because with the little bud earphones, and people are listening on their phones to music that is way too loud, and that can cause hearing loss as well. So this is just hanging out at a football stadium. This is noise at a football stadium. It's the Oilers, so obviously it's old data, right? But because the Oilers aren't around anymore. But notice that we're going. The sound is above 90 decibels almost all the time, and it goes up 110 decibels for the entire game from 6 to 9, and that's a lot. I mean, if you've ever gone to like a big sporting event like that, you usually come out and your ears are ringing because you've been exposed for quite a long time to very loud sounds. Babies. Also in 1998 created audibility curves for babies. We know babies can hear. As a matter of fact, newborns are all tested within hours of birth to see if they can hear. And basically what we do is we expose them to sounds and measure the responses of their brain, or measure the responses of their ears to the vibration of sounds. And we just want to make sure that every baby can hear, because sound is extremely important to the development of speech in human infants. So we can do audibility curves, as Also did, to see which frequencies and which sounds babies can hear. In 1980, DeCasper and Pfeiffer found that 2-day-old infants recognize their mother's voice, which of course is is easy to understand, because they spent several months in their mother's womb and heard the mother's voice. So 2-day-old infants have had a lot of exposure to mom's voice already, so they are able to understand it. So here's some data from Alsho's study. Basically what they did was they recorded a baby's face and and observers watched the baby and basically indicated whether or not the baby oriented toward the sound. And they found that they were able to build this curve of people, or observations of how children were, new 2-day-old babies were responding to sound. So there, as it got louder, the decibels, there were more and more responses of yes, that the child was able to hear this. I was able to detect that. I was able to tell that the child heard the sound. So you had a bunch of people rating babies and whether or not they heard something. These are audio curves for adults, for baby, using this technology, right? Now that we know we can do this, we can make these audio curves, right? So with adults, this is a typical adult plot. Of course, we can hear really well around this range, which is where we talk. But notice here, babies have roughly the same shape curve. It's just that they become more and more sensitive as they get older. So a 3-month-old infant is also most sensitive to that frequency range, but not as sensitive as an adult. And it probably has to do with the development of their ears, right? Their ears have to more fully develop before they can hear things better. And here's a picture of a little baby in one of these studies, and that tube that he's sucking on, they use that to measure response. So whenever the baby's just kind of bored and not paying attention to anything, it'll suck a lot, and then when it's looking at something that caught its attention, it'll suck less. So what they'll do is they'll use that sucking as an indicator as to whether or not the baby was paying attention to something or not. And I'll show you this video also. I'll put this online. It's we can use habituation to measure how long babies spend looking at things.